Hi guys, this is going to be a video about the energy transitions of hydrogen. Okay, so the energy levels of hydrogen, according to the Bohr model of the atom, right, are separated by just certain energies, and there aren't any energies allowed in between those energy levels. That's the quantization of the energy levels, right? He proved that by using the hydrogen spectrum, and he showed that there were no energies in between the energies where the electrons came out. Okay? And furthermore, what Bohr was able to do was he was able to conclude that the energy levels were separated by a distance that was proportional to its energy. And its energy was proportional to -1 over n squared, right? So if we had n equal to 1, n equal to 2, right? Let's say that this was a distance of 100. That means that the next distance would be proportional to 1 over n squared. And so n squared, right, that would be 2. Well, this would be proportional to 1 over 2 squared. Okay, so that's 1 over 1 squared, 1 over 2 squared. Let's say that was 1 over 3 squared, and so on and so forth, right? And so we actually knew what this constant was, right? I'm putting 100 here, but we actually knew exactly what that constant would be. And that is given by the Rydberg equation. Okay? This was an experimental equation that was able to calculate these energy transitions in between these different energy levels in hydrogen. It states that the inverse wavelength, 1 over wavelength, is equal to this constant r times 1 over the final energy level squared minus 1 over the initial energy squared. Okay? So the difference between these energy levels is given by the Rydberg equation. Okay? And so we can calculate the wavelength of light associated with these energy levels. Okay? For example, if we were going from n equal to 1 to n equal 3, okay? If we were going from the first energy level to the third energy level, right? Well, that means the wavelength that's associated with that transition, the inverse wavelength, is going to equal Rydberg's constant. And so Rydberg's constant r is equal to 1.097 times 10 to the 7th inverse meters. And that'll be given to you on an exam, right? So 1.097 times 10 to the 7th inverse meters. And so we're going from n equals 1 to n equals 3. So the final energy level here is n equals 3. The initial energy level here is n equals 1. Okay? What you'll notice is that this number is going to equal -0.89. Okay? -0.89. All right? Turns out this negative, that just means that we are exciting the electron. We're putting energy into this electron. All right? When we do our calculations, we aren't going to bother with the negative sign. We actually only really care about the magnitude of the number, so 0.89. All right? So, if we want the wavelength of light associated with this, well, we need to solve for wavelength. And the way we solve for wavelength is, well, if we take 1 over wavelength, right, let's combine these numbers. So we have 0.89 times 1.097. I'm going to quickly calculate that. So 1.097 times 0.89, and I get 0.976 times 10 to the 7th meter inverse, right? So, to get back to wavelength, currently we're at inverse wavelength, so to get back to wavelength, we're going to take it to the negative first power. Okay, so we're going to take both sides of the equation to the negative first power. What happens is, taking things to the negative first power flips this fraction. Okay, so denominators become numerators, numerators become denominators. So this becomes wavelength over 1, or simply wavelength. That's going to equal, since this is all a multiplication problem, we can split the negative 1, this inverse operator, to each of the terms. So 1 over 0.976, if we do that calculation, right, 1 divided by 0.976, we get 1.025. If we take 1 over 10 to the 7th, that's just going to be 10 to the negative 7th. Okay. If we take 1 over meter inverse, well, inverse and inverse cancel out, and so we're left with meters. Okay, so this is our wavelength associated with this energy transition. 1.025 times 10 to the negative 7th meters. Normally, we convert this to nanometers, and so the conversion factor here is that there are 10 to the 9th nanometers per meter, right? 10 to the 9th nanometers per meter, which means if we multiply this by 10 to the 9th, we get that wavelength is going to equal 102.5 nanometers. Okay? So the energy transition related to going from n equals 1 to n equals 3 is equal to 102.5 nanometers. All right? One final point, right? So if we look at the energy transitions, right? If we were asked which of these energy transitions has the largest energy, right? So for example, if we were comparing n equals 2 to n equals 4, n equals 1 to n equals 2, n equals 3 to n equals infinity. Where's that infinity coming from? And then n equals 4 to n equals 2, right? Well, how do we know which one has the biggest energy? Well, according to the Rydberg equation, 1 over wavelength is proportional to the difference in the squares of the energy levels, right? Well, we know that wavelength is proportional to frequency, right? Wavelength and frequency are very related according to this equation. We also know that frequency is also related to energy. Okay, so therefore wavelength has something to do with energy. All right, so we can actually use a form of the Rydberg equation to compare these, right? We don't have to do any of the multiplication with like the Rydberg constant and then convert to wavelengths or anything. We can actually just compare this difference here, right? 1 over n squared, nf squared minus 1 over ni squared. Okay, so this is the initial, this is the final, right? So if we look at these options, well, 1 over 2 squared minus 1 over 4 squared, if I calculate that real quick, right, so 1 divided by 4 minus 1 divided by 16, I get 0.1875. Okay? If I do 1 minus 1 divided by 4, I get 0.75. Okay? Again, I'm doing 1 over 1 squared. I'll write that explicitly, right? 1 over 1 squared minus 1 over 2 squared. That'll equal 0.75. 1 over 3 squared minus 1 over infinity squared. Infinity is just a really big number, right? So 1 over a really big number, right? 1 over a million, 1 over billion, 1 over Google, right? Well, this is actually just going to equal 0. Okay, so 1 over 3 squared is equal to 1 over 9, which is 0.11. And finally, n equals 4 to n equals 2, so 1 over 4 squared minus 1 over 2 squared, that's going to equal negative 0.1875. Again, we can just ignore the negative. So, right, this energy transition is exactly the same, going back and forth. Okay? So, which one has the greatest energy transition? Well, the one that has the greatest number. Okay? The greatest difference should give you the greatest energy transition. Right? And that makes sense, right? The greatest difference here gives you the greatest energy transition. 2 to 4 isn't as big as 1 to 3. See how big the step is for n equals 1 to n equals 2? Right? Usually n equals 1 to whatever, that's usually the biggest. But of course, you want to look at the math very carefully. Okay? So, the greatest energy transition would be this one. The least energy transition would be this one. Okay? All right. So, take care, guys.